for the next large mission surveys. Origins is on the left. Of course, there's Origins, Lynx, Habex, and LUVOIR. Everyone is familiar with these. The reports are out. I put the link for our report on the bottom. Being served by the decadal right now. Here's just the basic facts for Origins. It's a single aperture telescope, about 6 meters in diameter, cooled with cryocoolers for a long life, and it'll be at L2. Has 3 instruments in the current design. The thing we should always remember about for these large mission surveys, and Origins is no exception to this, is that these are the study designs for feasibility. If something like this gets put at the top of the queue for 10, 20 years down the line, a lot of this will change. I mean, this is not how it's going to fly. These are sort of proof of concept. So there's an Origin survey spectrometer, there's a far infrared imager, and there's a transit spectrometer for exoplanets. So it's really the OSS, which is the Origin spectrometer for the Origins mission, that's most interesting. It covers a wide wavelength range from 25 to almost 600 microns. It has low resolution spectroscopic mode and a very high resolution spectroscopic mode fed by an FTS. The low resolution mode is six gratings and slits. So it covers it'll cover a big area, and it's really a mapping telescope. It's really designed for mapping. Has very fast mapping speed. Just basics about some of the instruments here. It's not that important to know that in detail. These are our sort of science goals for the extragalactic part of Origins. So it's coevolution of stars and supermassive black holes, rise of metals over time. There's a lot of metal diagnostics in the far infrared. I'm not going to cover that. But again, I'm going to bring us back to this sort of basic theme of understanding the power sources in galaxies, including all dusty galaxies, and also being able to map large areas in nearby galaxies in far infrared emission lines, which are very good tracers of the low density gas like carbon-2. So those are the main themes of Origins. Origins provides a gigantic leap in sensitivity from every other infrared telescope that we've had before. Over 1,000 or more in sensitivity. It's amazing what you can do with a moderately sized telescope if you just manage to keep it cool. Think of a bit slightly bigger Herschel, but actually cold. There's a huge amount of phase space for discovery in that giant lozenge, in that red lozenge there. Here's some comparisons again. It's meant to map large areas fast, so you gain even more in mapping speed. And so part of our science case is Origins on the bottom there in the black is meant to derive large surveys of galaxies, understand the power sources in galaxies, and look for feedback. Here's an example of an infrared spectrum of a nearby galaxy that everyone has seen with all the lines marked, your star formation lines, your low ionization lines, your AGN lines of extremely high ionization, and the warm H2, which I mentioned the other day, which is a direct sign of feedback on the ISM in the galaxies. Origins sits pretty squarely between JWST and ALMA, the sort of missing wavelength range, which is very important for studying these sorts of features. Remember, JW stops at about 25 microns. There's an enormous gap in our coverage there that we can see for the next couple of decades. And that's what we designed Origins to sort of fill this gap. This is a little cartoon of the spectrum redshifting out. So we're going to do surveys. We're going to measure star formation rate and AGN power in thousands, if not millions of galaxies out to redshift 8. This is just one of our models of how many galaxies we're going to be able to see per redshift bin. There are thousands per redshift bin. We're going to map the baryon cycle in galaxies. And I just wanted to show a couple of examples to wrap it up. There's a simulated redshift 5 spectrum of NGC 6240, which is a ULERD with a powerful outflow on the upper left. That's an hour integration from our spectrometer. And on the lower right is a simulated OH far infrared absorption line spectrum from a galaxy like Markarian 231 at redshifts 2, 3, and 4. So we're going to be able to trace the emission from, let's say, warm H2 in the PAHs. We're going to see the absorption from these very interesting far infrared diagnostics of the very dense ISM that have been done very well for the nearby galaxies in the lower right with Herschel. And now we're able to carry that kind of observation out to redshifts of 4. And we'll be able to map, because we have these long slits, the actually diffuse low density gas in things like C2 in nearby galaxies. I'm just showing on the left some work we did with Spitzer and the PAHs and the fine structure lines in the mid-infrared. I don't have a good graphic of this for carbon-2. It's something we're really pushing hard with SOFIA right now, and is a main case for our for origins as well, to do a galaxy survey of hundreds of galaxies in the local universe, and map them in the carbon-2 emission, which gets down to insanely low densities of gas. So I think that's all I had. We don't need to look at the timeline because that's all aggressive and exciting, but as Chris said, this is sort of next decade, if not the decade after that kind of stuff. So we're pretty excited about the capabilities of origins, and I think it's relevant for the kind of science that we've been talking about, both in terms of the large-scale mapping of the CGM in nearby galaxies, but also doing these sort of surveys to sort of find these sort of actively outflowing and galaxies with strong feedback over very large scales, and completely irrespective of the dust content, which I think is pretty interesting. So I'll stop sharing and I'm done. Thanks, Carlos.
Great. Yeah. Thanks a lot, Lee. Really appreciate it.